Welcome. So, today is our lecture number 7. In this lecture, we are going to discuss about power stage design of basic switch mode power converters. So, in this lecture, we are going to cover steady state ripple parameters, derivation of RMS quantity, then selection of inductor, selection of capacitor, and then few simulation case studies. So, if we consider a synchronous buck converter, which we have already discussed, that means if we take a realistic circuit which include the on time of the so here which include the on time of this switch S1 the main switch, then on time of S bar, that is my the complementary switch, and this Vx is the switch node voltage terminal. So, before I start, actually I am going to show a few simulation case studies in which I set the parameter like a L equal to 2 microhenry, C equal to 500 microfarad, T equal to 1 microsecond, although this L I have taken quite large because we are operating at 1 megahertz switching frequency, but this is just to show a case study. In fact, we will want to see what is the effect of a larger inductor or a smaller inductor. So, we will take a few case studies. We took the DCR of the inductor like RL, then diode drop. If we here we are not operating in conventional buck converter, so there is no diode drop. So, it is set to 0. The on time of the MOSFET, the on time of the complementary MOSFET, then ESR of the capacitor, and we have also set some initial condition, and input voltage we have taken as 12 volt and the desired output voltage is 3.3. But since we are setting duty ratio directly without any closed loop control and there are parasitic drop, I will show you in ideal condition if we set the duty ratio, that means on time, what is the voltage gain of the ideal buck converter? Kv is equal to V0 by Vin. That means this is a voltage gain, and if we operate under like a steady state condition is a fixed switching frequency, then we can take this as my duty ratio and we will check whether we can get the desired voltage which is equal to Vref. Can we get it or not if we take D equal to Vref by Vin. Next, now in ideal simulation I have replaced here all these parasitic R1, R2, RL, which is the DCR of the inductor, then ESR of the capacitor, all are set to 0, just set to 0. And if we simulate this converter, and this I have simulated using MATLAB, and in fact I have discussed how to build blocks in MATLAB, using a series parallels in a parallel RLC circuit, series RLC circuit. But in subsequent lecture, we will also develop a simulating model, the model for realistic buck and boost converter, and we will also operate under different like a modulation and control technique. So, in this case we have used a fixed switching frequency which is 1 megahertz, and it is like a 1 microsecond time scale. You can see from here to here it is 1 microsecond, and here since we have considered an ideal case and we set the duty ratio D equal to, we have considered Vref by Vin, and for here we consider Vref to be 3.3 volt and Vin to be 12 volt. So, accordingly the duty ratio is set. Now, what you can see here, that this is my inductor ripple current, we call it as an inductor ripple current, this particular quantity, and if we take the average here, this is my average inductor current, and for this synchronous buck converter or this buck converter, it is nothing but the load current. And if we take the average value of this output voltage, it is almost 3.3, because we are talking about 3.2998, which is almost 3.3. So this is this value is our V0, that means the average value, and we are also discussing about this part, which is nothing but delta V0, that is my ripple output voltage. So we are concerned about, we are going to discuss what are the parameters like in inductor ripple, output voltage ripple, average inductor current, average output voltage, all this we are going to discuss. So these are the 4 parameters that we are going to discuss, and we want to see what is the effect of this parameter on these parameters if we incorporate the real component like a parasitic. So in this case we have seen that this waveform is waveform shows that the inductor current looks like a triangular waveform, and the capacitor voltage profile is also consistent, because we know that if the average, if we take the capacitor current, which is the subtraction of the inductor current minus load current. So that means if we want to draw the capacitor current, this will be same as inductor current if we eliminate the DC value. That means if we consider with respect to 0 value, if the dotted line is 0, and if the capacitor current is positive, the output voltage will rise, and if the capacitor current is negative, output voltage will fall. So this is consistent. The next, now we incorporated the parasitic. That means now we have considered RL, RC, and what we discuss in the the parameter set. These are the parameter set. Now we have incorporated those parameters with ESR, all this. So this is my ideal simulation which was shown earlier, and this is my practical simulation result of a practical synchronous buck converter, where we have considered ESR, then DCR, and on state resistance of the MOSFET. What we can find here, if we compare the 4 parameters that we discuss. What are the 4 parameters? One is the ripple inductor current. That means if we consider this ripple current, this is my ripple current. This is my ripple current. If we consider the ripple current like here to here, this is my ripple inductor current. What is my ripple inductor current? It is nearly 1.2 ampere. Output voltage that we discussed, and the ripple output voltage is almost negligible, because if you see from this value to this value, it is like a 0.0004, that means 0.4 millivolt, which is almost negligible. And what is the average value that we saw in that simulation? It is like around 16.5 ampere. That was our average value, inductor current value. The ripple we saw around 1.2 ampere, something like that, close to that. Now, what will happen, and what is the case? In both the cases, we consider D equal to Vref by V in, which is 3.3 by 12 in both the cases. You see, the ripple current in this case, that means if we take this ripple current, this remains more or less 1.2, that means this is almost same as 1.2 ampere. That means ripple current will not find much difference between these two waveform. But what about the average inductor current? The average inductor current, what is the value? It became 15 ampere. Whereas it was earlier 16.5, now it became 15 ampere. So there is a reduction is 1.5 ampere. What about the output voltage average value? So it is almost 3.018. whereas this was more or less, it is nearly 3.3 volt. So, there is almost a reduction of how much? Is nearly 0.2 volt, nearly 0.2 volt difference. So, the 0.2 volt, the magnitude, the output voltage is reduced by almost 0.2 volt. And what is the ripple parameter? If you take the ripple output voltage, so this is my ripple output voltage. This ripple output voltage is almost equal to how much? Around like a 50 millivolt, whereas this was around 0.4 millivolt. So, ripple current insignificant effect we can see from adding, like if we add parasitic. Ripple voltage, there is a significant effect, suddenly it has increased. The average current and average voltage both got affected significantly. And another point, if you see the profile of the output voltage, this looks like almost in phase with the inductor current. So, it clearly indicates that the contribution due to this ESR, which is into IC, this is now prominent, I mean this is the dominant effect. And since the capacitor current carries the ripple of the inductor current, because we assume the load current to be constant. So, the ripple current, that means the ESR into ripple inductor current, that ripple will appear in the output voltage as a dominant effect, and that is why it is in phase with the inductor current. So, what we can conclude from here, that in a practical converter, so we will have some we will have a significant effect of ESR. So, you have to carefully choose the capacitor, I mean we should reduce the ESR magnitude. Now, if we take the buck converter with ripple parameter, the inductor current ripple can be derived, if we take M1 to be the rising slope of the inductor current, this is a rising slope of the inductor current. So, I am talking about this quantity. So, this is nothing but V in minus V0 by L for a buck converter, and from where we can find out my relationship, like find out the relationship of the ripple inductor current. Now, if we continue, if we want to write, so what is known here in the previous equation? The output voltage we want to regulate. So, this is a fixed value. Inductor that we have chosen at the design cycle at the beginning, once we operate the converter, like once we design, the inductor value is more or less get fixed, although its value can change depending upon the amount of current it is flowing through it, because it will have some effect of nonlinear effect of the inductor, but in general we can keep that inductance value to be more or less constant. Now, we want to write the ripple parameter in terms of on time, off time, and here we want to write in V0 rather than V in. So, where the voltage gain is V0 minus V0 by V in, and voltage gain can be written as this on time, off time. So, you can write the input voltage to be V0, from where the inductor ripple can be written in terms of timing parameter, which is finally this. So, this is my delta IL. So, this is my inductor ripple. So, this can be derived, that means what it shows, the inductor current ripple depends on the output voltage, which we in this case we take this thing to be constant. Inductance value is almost fixed, we have already discussed, but now this is the off time. So, depending upon the off time, the inductance, the ripple inductor current can vary. If the off time increases, the ripple current increases. So, there is a trade off between ripple current and the off time, but off time is not in our hand because it depends on the voltage gain. Now, if we take the capacitor voltage ripple, again you can draw the capacitor current, and this profile is same as the inductor current, okay. But here the difference is that the average capacitor current at steady state should be 0, whereas the average inductor current in steady state is equal to I0, okay. So, we can find out our intention to find out this area under the curve during the positive charge condition, that when the capacitor current is positive. And it can be shown that this time is nothing but, this time period is nothing but T on plus T off by 2. So, this term is here actually, and this quantity is half of the ripple, which is this quantity. So, we are talking about this quantity, and area under the curve is half into height into the time. So, you can find out. Now, we know that IL is V0 by L into T off. So, if you substitute, then you can get the expression of the positive charge of the capacitor. Now, during this positive charge, output voltage will rise. So, you can replace that capacitor positive charge is equal to C into the positive voltage rise, that means the ripple voltage. So, the ripple voltage can be expressed in terms of inductor, capacitor, output voltage, and on off time, the ripple impact. Now, we want to see the worst case, we want to analyze the worst case current ripple, voltage ripple, and here we have considered pulse width modulation, but we can take other modulation also. So, under pulse width modulation, the total time period is fixed, on time is replaced by D into T on, D into total time, off time is 1 minus D into total time, and then current ripple can be written in terms of duty ratio. So, now if we look at this expression, the current ripple will be maximum when this duty ratio is minimum, and this is here minimum duty ratio. And in a buck converter, what happened under minimum duty ratio? That means, what is the, for a given output voltage, minimum duty ratio corresponds to the maximum input voltage, so highest input voltage. And if we take the output voltage ripple expression, it will also be maximum the output voltage when D is equal to minimum. We are talking about minimum duty ratio, and that will be minimum when the input voltage is maximum or the highest input voltage. So, the worst case voltage and current ripple will actually, we have to consider the worst case voltage and current ripple corresponds to the highest input voltage condition. Now, we want to find out the RMS quantity. So, RMS quantity of a periodic piecewise linear waveform. So, here we are talking about a piecewise linear waveform, that means in general it is like inductor current. Even this piecewise approximation is also valid for capacitor current, it is also valid for switch current, even if we consider diode current. So, these are valid. Okay. Now, even if the current is 0, this piecewise approximation is also valid. That means, under DCM, that means as long as the current waveform looks like with a linear slope, the slope can be 0, slope can be positive, slope can be negative, it does not matter. As long as it has a linear slope, any periodic waveform with linear slopes, it can be represented, the RMS value of this waveform can be represented by 1 by T, particularly for this waveform. X1 is the value of this waveform at t equal to 0, and it is x2 when t equal to t1 after the interval of t1. Then after second interval, it is x2 here, t2, that means this is my duration t2, this is my duration t1, and this is my duration t3, which is nothing but capital T minus t1 minus t2. So, it can be represented by this. How can you prove that? Okay, I am just giving a hint, although I am going to prove it in the next slide. So, if we take the RMS current of this periodic waveform, and here for a special case we are talking about a periodic waveform with piecewise linear approximation. It is shown, it looks like a piecewise linear waveform. In fact, this piecewise linear current is common in many DC-DC converters, whether it is isolated, non-isolated, in various other converters also. As long as we can get a piecewise linear current approximation, we can apply this formula. If there can be n number of interval, more number of interval, does not matter. So, as long as it is a periodic waveform and piecewise linear, this is valid. Now, if you want to get the RMS square, this is a basic equation, 1 by total time, then integral 0 to t, the time period, x square t dt. Okay. So, you can break this, the whole integral, into 3 pieces, because there are 3 regions, the region 1, region 2 and region 3. So, this corresponds to region 1, region 2 and region 3. Now, this is a definite integral. So, we can change the, in the definite integral we can change the interval limit, that means the integral limit, and accordingly we have to update this time. So, the same thing we have just changed the integral limit, and in the next slide we are continuing with that RMS waveform with the integral limit that we have already discussed. So, now each region like R1, R2, R3, that means this particular equation corresponds to R2 and this corresponds to R3 region. That means we are talking about this region to be R1, this region to be R2 and this region to be R3. Here, if we take a generic expression, that means if we take a generic region where the integral for that particular integral, for that particular region, the integral is 0 to tk x square to dt. Let us say this is my, this duration is my tk duration, where the starting value here is my, let us say it is xk, and the final value of this duration is xk plus 1. Okay? So, that means this waveform, the starting value, that means what is the equation of this waveform during this interval? It will be xk plus the slope of this waveform mk t, and this is during the interval t equal to 0 to tk. What is the slope? The slope mk is nothing but its final value xk plus 1 minus xk divided by tk. So, this is my time period. Now, this slope can be positive if xk plus 1 is larger than xk. The slope is negative when xk plus 1 is smaller than xk, and it can be 0 when both are equal. So, it does not matter whether it is positive, negative or 0, but it should be constant. Now, if you take this slope then and then this xk plus 1, so this corresponds to my mk that we have represented. So, you can write, and this corresponds to my x of t during the interval 0 to tk. Then if we write the full expression of this square term, because there is a square term here, and then if we integrate, after computing the integration, we will get this expression, and after simplification we can get this final expression. So, that means if we take this x square t during this interval tk interval, we will get this value, and this is nothing but xk square, xk into xk plus 1, then plus xk plus 1 square by 3 into tk, that is the duration of the interval. And this we can compute for this interval also. So, I can take that I3, I can calculate I2, I can calculate, this is my I1. So, this integral I can compute for different region. Okay. So, then the RMS current, which was our original expression, that can be written as the sum of this integral. That means I am talking about, this is my I1 this is my I1, this is my I1, this is my I2 and this is my I3, and if I add them and divide by total time, then we will get x RMS square. So, x RMS square, and this is what we have actually written at the beginning. Now, we want to compute this for the inductor current. For the inductor current, it has only two interval, like this interval and this interval. What is this interval? This interval is on time and this interval is off time. In the beginning, the value is I1 at the beginning and the final value is I2. For this interval, I2 is the initial value and I1 is the final value. So, then what is delta IL? That is the ripple current, that is the I2 minus I1. So, I1 is the peak, this corresponds to peak current and this corresponds to this I1 corresponds to the valley current, this corresponds to the valley current. So, we can find out the ripple current in terms of peak and valley, and we can get the peak and valley expression in terms of delta IL. We can also get the average inductor current in terms of this quantity. Why it is important? We have to find I1 and I2 in terms of average inductor current and the ripple current, how they are related, because we want to find out the RMS current. The RMS current is what? We know the formula 1 by total time period. Then in this case I1 square, I1 I2, I2 square by 3, and since both I1 and I2 are common for both the interval, only there whether in one case it is peak and a valley. So, like beginning value, but it does not matter as long as this formula is concerned. Then the total time is T1, it is common for T1, the same expression, it is also common for T off. So, if we add them together, then we will get the IL RMS current is I1 square plus I1 I2 plus I2 square by 3. If you substitute the peak and valley current in terms of their average current and the ripple current, then you will get I RMS square is IL square by the average inductor current square plus the ripple current square by 12. So, in buck converter, the average inductor current is same as the average load current. So, we can summarize that RMS current for a buck converter is the load current square plus the ripple current square by 12 for a given load current. That means, if this is constant, IL RMS, that means the RMS inductor current increases with the ripple current, and it is maximum when the ripple current is maximum, and that is maximum at the maximum input voltage that we have discussed. This is particularly important for estimating the conduction loss, because if the RMS current is more, then the conduction loss will be more. So, higher RMS current will lead to higher conduction loss. Now, for a given input voltage, if input voltage is given, now the load current is varying. So, the RMS current increases with delta IL. RMS current it should increase with the load current, because for given input voltage, given output voltage, the RMS only load current changes, the ripple current remains more or less same. So, if the load current changes, it increases with load current. So, higher conduction loss at higher load current, and the worst case RMS current will be at the highest input voltage and the highest load current condition. So, that is the worst case condition for the RMS current, and this is also important. That means, in this condition, at this condition, our conduction loss will be maximum. So, the design consideration, we understood the RMS quantities. Now, we want to discuss that should we choose a larger inductor or a smaller inductor. So, it is clear from the previous expression, if we take a larger inductor, then the ripple current will get reduced, because and if the ripple current get reduced, then the RMS current get reduced. So, we can save some conduction loss, that means we can reduce conduction loss, but the inductor size is increasing. But we also want to see, that was the steady state effect, we want to see what is the effect in the dynamic performance. So, here I have simulated a case study. Again, this is the case study of a practical synchronous buck converter, where we have set the duty ratio D equal to Vref by V in, and which we have taken D equal to 3.3 by 12. Since there are parasitic drops, so the output voltage is not maintained at 3.3 volt because there is no feedback loop. So, it will be less than 3.3 because of drop, and you will see this drop will increase at higher load current when the output voltage average value further decreases. That means, if you take this point and this point, there is a reduction in the, there is a shift in the DC shift, there is a DC shift, and this DC shift is to the more drop across. That means, inductor DCR, the on time resistance of the MOSFET, this can be anticipated by closed loop control by adjusting the duty ratio, but here we are working or here we are operating at a fixed duty ratio. But what is our interest here? Our primary interest to see the average inductor current and the ripple inductor current. So, you can see the red trace corresponds to the value when L large, that means larger inductor, and it is consistent that we are getting smaller ripple, but average is independent of the inductance value, and average voltage also remains same for two different value of inductor, and the blue trace corresponds to L small, smaller, it is larger. But what is more important, if you see this undershoot, that means, if you compute from this value to this value, delta V0. So, this delta V0 is larger, that means, I am talking about this steady state point, is much larger for larger inductor, and it is smaller for smaller inductor because this value is much smaller. And also, if you see the settling time, that means, that means how long it takes to come to steady state, that also increases. So, for larger inductor, our settling time is more, and delta V0 undershoot is also more, and this can be reduced using smaller inductor. That means, the choice of inductors is also important in terms of dynamic performance. Okay. So, the design consideration of the inductor, if you take a large inductor, the advantage will be you can reduce the ripple parameter, you can reduce the RMS current, so you can reduce the conduction loss, and you can also reduce the output voltage ripple. What are the disadvantages? That means, the inductor size will increase naturally because you are taking a larger inductor, the value of the inductance is high, and we saw that load transient response is slower. There is a natural response of the converter. So, if the natural response is slower, that means it indicates that when we design controller also do small cell analysis, this will be reflected in the control to output transfer function, and it also lead to higher overshoot and undershoot, and those things cannot be avoided if you use a larger inductor. Even with a closed loop control, the relative undershoot for a larger and smaller inductor, that relative reduction using a smaller inductor, that concept is it remains same even under closed loop condition. That means, using closed loop you can reduce the inductor, the output voltage undershoot by using a smaller inductor. So, inductor should be carefully selected. For capacitor, if we use a larger capacitor, naturally the output voltage ripple will get reduced, this is obvious, and we can also reduce the output voltage undershoot by choosing a larger capacitor, but the larger capacitor size will increase, and if the size increases in capacitor, the reliability issue also become important because it is more prone to failure, the larger capacitor. And also we have not discussed here, in future we will discuss, a larger capacitor require more energy when we want to change the voltage of the output voltage of the DC-DC converter. This is important for dynamic voltage scaling, even it is also important for DC link voltage, shifting of DC link voltage of a DC-DC converter. So, larger capacitor require more energy for shifting from one voltage level to the other voltage level. So, it will increase energy overhead as well as time overhead. So, we have to select capacitor carefully. Ripple inductor current of a boost converter can be derived in a similar way of a buck converter, by finding the rising slope, then and expressing in terms of input output voltage. So, for a boost converter, the ripple inductor current under pulse width modulation, the process is same as earlier, only you have to formulate the, you have to find out the ripple current in terms of the output voltage, inductance and the duty ratio. And it is interesting to see in this case that inductor current ripple, when the output voltage is constant, is maximum if you differentiate with respect to duty ratio, it is maximum at D equal to 0.5. So, in a buck converter we got the current ripple is maximum at minimum duty ratio, but for a boost converter it is maximum for 50% duty ratio. Either side of the duty ratio you can reduce the inductor current ripple, it is maximum. If you look at the output voltage ripple, then the capacitor current can be replaced, it is actually the minus of load current when the switch is on and switch is off, it is IL minus I0. So, you can find out if you take this negative interval, that means we are talking about this area under the curve, then what is the area under the curve? I0 into T on is equal to delta V0 into C. So, this is my undershoot or basically negative ripple, that means how much it is deviate. So, output voltage ripple can be expressed in terms of load current and the on time. So, you can find out under pulse width modulation, the output voltage ripple is maximum at maximum duty ratio, it is also maximum at maximum load current. So, the worst case output voltage ripple will happen at highest load current condition and highest duty ratio, that means the lowest input voltage condition. So, this is different from the buck converter example. So, we found the ripple voltage ripple current for buck and boost converter, we found the RMS current. In the similar manner we can find the RMS current for a boost converter and we can analyze that under what condition the ripple current is maximum. So, here we have taken only pulse width modulation, but we can also consider other modulation technique. So, in summary, we have discussed steady state ripple parameter, we have considered the important design constraint. RMS current formulation also have shown, like and how it is going to affect the conduction loss, and as a result consequently the effect will appear in the efficiency also. The selection of inductor is discussed, that means it is a trade off between the steady state RMS ripple parameter as well as the transient response. The selection of capacitor is important, that in terms of ripple parameter as well as its reliability. So, we have to carefully design inductor and capacitor. So, the power stage design is very critical and it has to be designed not only from steady state standpoint, we should also keep in mind the transient point of view. With this, we want to finish today's lecture. Thank you very much.